Welcome and good evening. My name is Anne Hughes and I will be your host for this evening's educational session. I'm the account manager for ReaCare and I can be your point of contact for any support queries you may have after this webinar. We appreciate you taking the time out tonight to join us. Tonight's event is brought to you by ReaCare. ReaCare are the exclusive distributor of Econia's lasers technology in Australia and New Zealand. And for more information about the EVRL laser that we are introducing tonight, please visit our website, www.reacare.com.au. Before we begin, I would like to acknowledge the traditional custodians of the land on which we gather today and pay my respects to their elders, past, present and emerging. I extend that respect to Aboriginal and Torres Strait Islander peoples here today. I would also like to acknowledge the traditional owners of the lands which you are on today. Without further ado, please welcome Brett Jarosz. Over to you, Brett.
Thanks, Anne. Okay, good evening, everyone. So webinar 2, following on from last month's webinar 1, where what we want to try and do today is expand on that science and information that we introduced, and I want to use that word introduction, in webinar 1. And today we really want to try and expand on that science technology so we can help understand the differences between the various forms of photobiomodulation therapy, the different technologies. And then we want to get into more of the evidence-based applications of low-level laser therapy, specifically as it relates to the EVRL. So just my disclosures, the same as last time. I'm not an employee of Econia or ReaCare. I'm a consumer of their products that I use in my clinical practice. I may get paid an honorarium or commission from certain vendors, depending on my speaking engagements with them. And the important parts, of course, the presentation is not intended to diagnose, treat, or cure any medical disease process. This is going to be especially relevant when we get into webinar 3 next month, when we start to go through further advanced applications of low-level laser therapy. And then when we look at just certain treatment applications, especially for next module, they may be used off-label in relationship to FDA approval, but all topics presented have research to support the treatment applications. The ones we're going to go through today are just categoric evidence-based level 1 trials. And as always, remain within your scope of practice, whatever your qualification and your particular region of registration for your practice. So, webinar 1 we covered last month, and then today we're going to be breaking down those differences in technologies between laser, between infrared, between LEDs, and we really want to go through those different scientific mechanisms, and we really want to bring clarity to where we look at even the literature. We want to look at the information, say, with how marketing with different laser companies, light therapy companies, how that marketing can provide a little bit of confusion, misinformation. We really want to become clear on understanding what each of the technologies are and do, with a bias towards understanding that low-level laser therapy a little bit more. So tonight we're going to go through the review of those scientific mechanisms from webinar 1. We'll go through those differences in technologies, and we really want to break down a lot of these sort of key questions and arguments that exist out there: wavelength versus depth of penetration. The important one, the takeaway I really want to have from today, is this photochemical versus photothermal. And then I guess the big debate, power versus energy, you know, the watts of the laser we're using versus energy. And this is going to tie in very much to the photochemical effect. Then the difference between coherence and non-coherence, really we're talking about lasers versus LEDs there. And then we want to talk about class 4 lasers in particular, because they're sort of some of the bigger brands and bigger names that we know. So we want to understand the differences between those low-level laser and LEDs. And then we'll go through the Fda clearances that exist for Econia specifically, as well as for the different, diseases, pathophysiological processes, conditions, etc. And then we'll go through those evidence-based clinical applications of low-level laser therapy using the EVRL. So I've got a lot of slides to get through. We've got again, breaking the laws of presenting here tonight. So we've got way too many slides in shorter period of time. But the reason I'm doing it is as I went through this journey and my process of starting to understand more about photobiomodulation and what that encompasses, I'm sort of delivering this material in a way that actually helped me to understand how all of these things worked. Because I was confused and I was seeking lots of clarification. I was getting confused within the research, within marketing, with what was available online. So I've got to deliver this information. If we're running a bit over time tonight, I don't mind staying back and answering people's questions where I can. If you guys have to go, obviously at the end of the hour, I understand that, but this is being recorded and we're obviously going to be able to have access to that recording. So I'll go at a pretty decent clip. Everything, as you know from last webinar, I reference everything. So you'll have all those references as well that you can refer back to. So the review from webinar 1, we said the first law of photobiology is that for low power visible light to have any effect on a living biological system, photons must be absorbed. So we talked about in webinar 1, the absorption of the photons from the light versus scattering. Okay, so they have to be absorbed, and that we needed to have something within that living organism, that living tissue, that allowed those photons to be absorbed. And then we mentioned that the energy of an individual photon depends only on the wavelength. We're going to really expand on this one tonight. So take that one, put it in the front of your mind, not in the back, but in the front of your mind about the energy. We talked about it earlier. We're going to try and break the difference down between power versus energy. But first hint there, energy has to do only with the wavelength, so the color of the light. So the color of the light is what determines the amount of energy. So therefore, the energy of a dose of light depends only on the number of photons, the color of the wavelength. So the example there, as we can see in the picture on the left, so when we come over to the actual colors here on the bottom, we can see there's your visible light spectrum there. We can see increasing energy as we get towards the blue, decreasing energy as we get towards the red. So blue photons have more energy than green, that have more energy than red, that have more energy than infrared. All right, so the visible light spectrum, blue down here, red down here, infrared here, as we can see UV, the sun, etc., X-rays, gamma rays, and away we go. We talked about in webinar 1 that low-level laser therapy inevitably affects the mitochondria. We broke that down in webinar 1 to talk about how red wavelengths and that red light has an apparent mechanism on complex 4 within the mitochondria. So we can see that here. We talked about this as cytochrome C oxidase or COX. So our complex 4 red light appears to have the effect of being absorbed by COX. That's the chromophore in complex 4. And that is what absorbs the red light to have then that photochemical effect. So we talked about how the literature shows that low-level laser therapy works by photodissociating nitric oxide from COX, which then allowed that resumption of mitochondrial respiration, so basically the production of ATP. And we talked about low-level laser therapy produces a shift in overall cell redox potential in the direction of greater oxidation. So the end process is light absorbed by a chromophore, which seemed to be the red light in complex 4, that chromophore being cytochrome C oxidase. With that absorption, we want to break this down and how we understand how these electron transport chain works. Obviously, some thought processes may have occurred for some people going on, not that stuff again. But we just want to go through some overview so we actually understand how light induces this energy that causes electrons to jump, and that jumping of electrons is what causes this donation of the electrons into that electron transport chain that allows us to be able to produce ATP and enhance cellular function. And then the other important one we talked about towards the end of last webinar was this biphasic dose response. So as we can see there in that particular picture on the right, showing the difference between biostimulation, bioinhibition, and obviously detrimental effects. So not much happening. we get biostimulation reaching a maximum effect, and then we start to go into bioinhibition, and then of course now we're into detrimental effects down here. So what the biphasic dose response suggests is that if insufficient energy is applied, there will be no response, which of course is showing you this down here towards the 0, because the minimum threshold has not been met. So there's not enough energy. Again, that difference between energy and power, there's not enough energy. If more energy is applied, then a threshold is crossed and biostimulation is achieved. So that's obviously the upward curve here of that red graph. But when too much energy is applied, then stimulation disappears and is replaced by bioinhibition. So this applies, of course, to drugs. And just a hint here now, when we talk about drugs and pharmaceuticals, we're talking about biochemistry, whether we're talking about supplements, nutraceuticals. Again, we're talking about creating something in a dose range that has this stimulatory effect. But if we know if we overdose on particular drugs, so let's say we're taking Panadol, paracetamol, and we've taken that because we're in pain, whatever the tablets say is 2 every 4 to 6 hours is what you're allowed to take. So if you go, well, I'm awake for, say, 24 hours for the sake of math, you go, well, that means I could take the drugs 6 times. So we wouldn't take 12 of them in one go, even though that's the dosage, because that, of course, could create overdosing and bioinhibition. So the same thing applies to light therapy, but instead of biochemistry for pharmaceuticals and nutraceuticals, we can talk about photochemistry in the context today of low-level laser therapy, LEDs, class 4 lasers, etc. So let's get into the differences between these technologies. Now, where we want to start here is this term, Photobiomodulation Therapy. So it was established in 2015, and it was defined as a form of light therapy that utilizes non-ionizing forms of light sources, including lasers, LEDs, and broadband light in the visible and infrared spectrum. Now, the reason they brought this terminology in was to try and bring greater clarity to the field of all the forms of different light therapy. Now, I just want to bring up an article that got published 2020 in a decent journal here in Australia. And it was, photobiomodulation therapy does not decrease pain and disability in people with non-specific low back pain, and it's a systematic review. Now, systematic reviews, of course, are our highest level of evidence, along with obviously meta-analyses being on top, but we're talking about highest level of evidence here. And it's stating that photobiomodulation therapy doesn't help people with non-specific low back pain. Now, the problem with this, and it's being published in the literature, and we're supposed to go to the highest forms of literature, is they are using the word photobiomodulation. In their systematic review, they were able to include 12 RCTs, and the conclusion from those 12 RCTs is that current evidence does not support the use of photobiomodulation therapy to decrease pain and disability in people with non-specific low back pain. But the point I wanted to show you there is when you go and read the article, the wavelengths there that they used, as you can see, 808, 810, 820, 830, 850, 904, 1064, these are all infrared wavelengths. That doesn't encompass photobiomodulation therapy. That is just infrared wavelengths. So now we've got a little bit more confusion in a high-level published journal, and the word that's being used doesn't define that. So that doesn't include necessarily LEDs. That doesn't necessarily include all low-level laser therapy, because we've got all these different other wavelengths. So we can see that there's already confusion even within our highest form of literature, because we've got terminology there that's going to confuse the consumer, whether that's us as a practitioner or whether that is the patient that's trying to seek the appropriate treatment for whatever condition they've got. So then if this is just from today, so I just went and plugged this into PubMed today and just typed in low-level laser therapy and placebo-controlled trials. And as we can see, for low-level placebo-controlled, we've got 522 articles. And for class 4 lasers, placebo-controlled, we have 7 articles. So then again, we've got this other confusion, everything being encompassed into photobiomodulation therapy. We've got low-level laser therapy, we've got class 4 lasers, we've got LEDs. So we want to really try and start to understand the differences between these. And the first thing is the terminology. and you jump into the research and you start having a look at this, just like I did at the start, we can get a lot of confusion. So I want us to understand the basic mechanisms behind all forms of light therapy first. And then I am of the opinion it's going to allow us to better understand the research when you read it and what the research suggests from what's efficacious and what's not. Because then I want to talk to you about like how FDA clearances are achieved and how Erconia got all those FDA clearances, because they are level 1 randomized, double-blinded, placebo-controlled trials. So when we start to look at that, we can see that there's issues within the processes of research too. Okay, so the parameters of low-level laser, and these are our arguments: wavelength versus depth of penetration, photochemical versus photothermal, power versus energy, coherent versus non-coherent light. So let's jump into the first one, wavelength versus depth of penetration. So photon energy, and I want to talk about that word again, energy. We're really joining two sections together with energy and power, but energy and wavelength are tied together. So photon energy is measured in electron volts. That's just the terminology. The shorter the wavelength, so if we look at the picture again here, over here we can see with the gamma rays, we can see these wavelengths are shorter and the wavelengths start becoming longer as I move over to the left towards the radio waves. So the shorter the wavelength, the higher the electron volts, the higher the energy. And so that makes sense if you're into the whole Marvel, Bruce Banner, you know, the whole gamma rays. So we can see here X-rays that obviously a lot of practitioners that are online here tonight familiar with, either referring for or reading. Then we've got our UV, of course, for our sun. We've got our visible light spectrum, and then we move into our infrared, our microwaves, and our radio waves. So we can see here that the nanometers we can see in here. So in this violet range, violet blue, 405 nanometer is 3.06 electron volts. Then we get to this 532, which is getting into this emerald range, 233 electron volts. 635 is the red from Erconia. So all of these, by the way, 405 is the violet from Erconia. This 532 is in this emerald green from Erconia. 635 is the red from Erconia. And then our 830 nanometers, that sort of standard range of infrared. So we can see the differences in the electron volts. We can see here that 405, the violet wavelength, has 70% more energy per photon than the infrared wavelength. But I want you to sort of remember these numbers. I'm going to remember them for you. But if we look at that 1.49 for the infrared and 1.95 for the red. So we just use these two as we go into some research a little bit later on about what this photonic energy, what these wavelengths do from a cellular process perspective. Now, I'm using this one as a very sort of, I guess, create a picture in everyone's mind about this idea of depth of penetration, because a lot of people will start to talk to you about you need power. You need to have your 40 and 50 watt lasers to get the photons or the light to be able to penetrate. And we'll talk about this more as we get towards the end of today's actual lecture. But if we look at this picture here on the left, so I just got a couple of things popped up. Oh, cool. So when we look at the picture on the left, we're looking at the different forms of wavelength here. So we can see around that 800, that infrared, we can see the red. Now, as you can see here, they've separated the colors here just for visualization. So we can see all these different colors and we can see the actual penetration into water. Just think about it. The deeper you get into the ocean, the bluer it becomes. And that's because the blue wavelength can penetrate deeper. And then we can see with those different colors, so you think of the ocean, it's bluey, it's green, and then start to think about, is the water colder at the top or is it warmer at the top? And of course, we all understand that the water's warmer at the top and the deeper you go, the colder it gets. And so we'll start to understand this reason why. So the visible light doesn't get absorbed by water. Now, I brought this point here because it's just obviously this PhD guy suggests that the human body may be 99% water. most of the stuff that's out there suggests that, you know, we're 70% water. And that's why I want to bring this point up with this depth of penetration and our different wavelengths and energy. So water absorption. Water doesn't absorb in the wavelength range of the visible light. Okay, so a visible light spectrum, we can see over on the picture here, infrared here, UV here, but our visible light spectrum, so that 400 to 700 nanometers, it's too energetic. All right, we talked about that range being about 1.95 there for the Oconia red to 3.06 electron volts for down in that violet. It's too energetic for the vibrations of the water molecule, but the infrared light spectrum exhibits strong absorptions from vibrations of the water molecule, and the result is infrared absorption is heating of the tissue because it causes increased molecular vibrational activity. So this is our photothermal effect. So visible light penetrates, infrared light is absorbed by water. So we think about those that have used class 4 lasers, or maybe have heard people talk about class 4 lasers, and people have to keep moving them because of that photothermal effect, because it's heating tissue. How is it heating tissue, of course? Well, our skin and the dermis is about 95% water. So when you shine infrared light on the skin, it's being absorbed in the dermis. And of course, that causes those vibrational, rotational, molecular aspects, which is then a photothermal effect, which causes the heating. So when we put infrared on ourselves, we get that heating effect and that photothermal effect. So getting into this next section where we'll lead into here, photothermal, we've got our infrared wavelengths get absorbed in water, causing that vibrational effect in the water, which creates the photothermal heating effect. Then if we go back to the depth of penetration aspect, that visible light was too energetic to be absorbed by water. So photochemistry now, so infrared photothermal, photochemical, we know that visible and infrared affect biostimulation in different ways. Visible light elicits photochemical changes, whilst infrared can only produce physical changes, i.e. those vibrational, rotational, molecular aspects which create the heating. Although visible light can produce photochemistry, infrared light only produces molecular rotations and vibrations. And this was the point I said on those slides earlier. Considering the low quantum energy per photon for the 685 to 905 range, which is infrared, that equals 1.52 to 1.3 electron volts. I showed you on that slide earlier, it was around that 1.4-ish. They apparently do not induce direct photochemistry, as the minimum quantum energy is in the order of 1.7. So we said the red is about 1.95 electron volts. And then as you can see here, the infrared range is about 1.52. So infrared creates photothermal effects, and our visible wavelengths create the photochemical effects. So let's break those two aspects down a little bit more, photochemistry versus photothermal effects. So what is photochemistry? It deals with the chemical reactions which occurred by the absorption of light waves. So we talked about that in webinar 1. We reviewed at the start. We need the actual light to be absorbed. Or he said infrared's absorbed by water. So we need, as we said, some form of molecule to absorb the visible light, a chromophore, as the example we talked about before, to impart its photochemical effects. So the photon should contain sufficient amount of energy to raise molecules to an excited state. So I hate doing this. We're going to go to a slide in a minute where we're going to have the atom again, and we're going to have the idea of the nucleus. We're going to have the orbital rings, and we may remember that, the idea of the periodic table, right? Hydrogen, helium, lithium, beryllium. We've got all that idea of the 1 and the 2 and how many pluses that we have on those outer shells of those different types of electrons. So I don't want to get into a huge physics, chemistry sort of review, but we just want to hit those high points to get that understanding of how visible light is having that photochemical effect. So we need the photons to have a sufficient amount of energy to raise the molecules to an excited state. And when a molecule absorbs a photon of light, it becomes electronically excited. This electronic excitation can result in breaking, reforming, and thus rearrangement of chemical bonds, as well as electron and energy transfer between various parts of a chemical system. And as we said, we can't achieve that with infrared light because it's being absorbed in the water, as we said, creating those physical photothermal effects. But the important part there is to understand that the infrared, the electron volt that it has, doesn't have enough energy to create a photochemical effect. So summary, infrared is photothermal, visible light is in that photochemical aspect. Again, just another picture again, talking about the same thing. So if we look at the visible light is strongly absorbed because it causes electron jumps to higher levels and it's not enough energy there to be ionized. But the infrared has stronger absorption, vibrates molecules, physiological effect is heating since it's putting molecules into vibrational motion. All right, photochemical versus photothermal. And again, we're talking about that energy, wavelength, the color of the visible light. More towards violet we get, the more energy that the actual wavelength has, the more electron volts. So here it is, all right, the horrible slide. So low-level laser photochemistry. For a photon to be absorbed, the energy, the electron volt of the photon must match the difference between the energy between the orbits of the electrons in order to move to a higher state. So energy levels of all atoms to allow electrons to move to higher orbit, the wavelength must be between 380 nanometers and 683 nanometers. So if we look at the very bottom, what we can see there is some of the common elements there. So molecule absorption wavelengths, necessity to move electrons to a higher state. So obviously we've got our calciums, our hydrogen, ions, etc. And as we can see through the different colors here, we can see the nanometers, the wavelength, the color of the light, saying all the same stuff there, in order to be able to move the electrons to a higher state. These are the wavelengths that are required. So just used a sort of a simple picture over here, obviously where we can see that the red wavelength is going to allow this one jump. So remember we talked before about how, right, you can see the violet here jumping 1, 2, 3. All right, so it's jumping 3 rings. And so moving from that 5th ring to get to the 2nd requires roughly 3.4 electron volts. For it to move 1 and 2, you can see from 5 into 3 requires about 1.5 electron volts. And then to move 1 ring in from 5 into 4, we need obviously a little bit less. So in summary there, we can see that violet excites around 3 levels with its 3.06 electron volts. Blue-green excites about 2 levels, and red excites about 1 level. And this donates the electrons to the electron transport chain. So if you go and have a look back at our whole ATP production, the Krebs cycle, mitochondria, etc., and we go through that whole process of our different complexes, we'll have a little summary slide coming up soon, and we can see just that overview of how we need that photonic energy to excite the electrons, get them to a higher state. That higher state donates the electrons to the electron transport chain and stimulates that mitochondrial respiration. So in principle, one photon can activate one enzyme molecule, which in turn can process many thousands of substrate molecules. If the effect of one photon can be amplified biologically, then one does not need a lot of photons to produce an effect. One just needs to find the proper wavelength of light to stimulate the proper enzyme, which in turn will stimulate the beneficial therapeutic effect. So we showed you in webinar 1, the idea of red light stimulating cytochrome C oxidase complex 4. So the red wavelength had this affinity for obviously COX within that complex 4. So finding the right wavelength, and this is some of the, I guess, the research and scientific brilliance of Erconia. And again, disclosure's biased, I'm using their products, but hopefully through these presentations, I think you'll start to understand why I've become biased to their particular products, understanding the science behind it. And you see those guys as a company that have done the research they have behind these wavelengths. So here's this idea now of understanding the different wavelengths and then the electron transport chain. So what they're starting to show is this. We've known for quite some time now, since the 60s, when we had the helium neon laser, and how that was first experimented on the rats with the shaved back, tried to use light therapy to see if it would induce cancer, and then they discovered that the actual hair grew back on the mouse quicker, and then that sort of discovery got then expanded into wound healing in humans. And then a lot of the research here, obviously with the red wavelength and the understanding of complex 4 with cytochrome C oxidase. And we can see here, what it's showing is that idea of the electrons jumping into that higher energy state. So showing here that using a violet or blue light, then impacting complexes 1 and 2. And so for a lot of us that maybe use nutraceuticals, we can see here, Coenzyme Q10, a lot of us use that for patients who are struggling with fatigue, for energy. And so we say, yeah, take some CoQ10, because what we're trying to do here is help stimulate that electron transport chain, that respiration within the mitochondria to produce ATP. And so laser itself is actually photochemically stimulating that. And of course, when you look at the idea of violet and blue light stimulating complexes 1 and 2, and then enhancing this electron to be enhanced in 1 and 2 across to a higher energy state, you can see here now how we're going to be able to get more benefits by the combination of violet and red wavelengths, and previously understanding that electron volt energy. So let's go into that next sort of concept that comes up, and the queries that come up a lot, the difference between power versus energy. So what does increasing power change? So when we think power, we're thinking the wattage. So when people talk about, I've got a 5 milliwatt laser versus a 10 watt laser versus a 50 watt laser, what we want to understand is that when you've got, let's just say, every single device we're using right now has got, just for argument's sake, keep it simple, 600 nanometer, or let's go 635, the 635 red wavelength. So I've got the photonic energy of 635 coming out with that color of wavelength. So 1.95 electron volts of energy. By adding power to the laser, what you're doing is you are having more photons emitted. So all you're doing is you're getting more and more buckets of the same wavelength. Okay, so I've got a bucket of 635 nanometer red, and that's my just standard laser, and I'm throwing it. But now, for the argument's sake, that's my 1 watt laser. And then a 10 watt laser would now have 10 buckets of that same wavelength. It doesn't change the energy. The only thing that changes the energy is the actual color of the wavelength. So I would need to obviously decrease the nanometers to have more energy. So 635, I'd need to take that down to 600, to 500, to 400. And of course, that's changing the color of the wave. That's how we change the energy of the photon. Increasing the power does not increase depth of penetration. That's just getting the 10 buckets. And so if I'm throwing the 1 bucket at my head, throwing 10 buckets at my head doesn't change it penetrating any deeper or shallower. What we're dealing with, it's the wavelength that creates that, I guess, the depth of penetration. But it's go into the research, which I haven't done in this presentation, but it's not even the question really of the depth of penetration. When we look at the cellular processes, it's all got to do with this whole photochemical effects that the wavelengths are imparting. So biostimulation's been reported in the literature. So let's go back to that biphasic dose response, the Arndt-Schultz law, or the hormesis in modern terminology. So if we go back to that biphasic dose response, that we know that we've got a biostimulation, maximal effect, and then we go into bioinhibition, detrimental effects. So biostimulation's been reported in the literature with doses from as low as 0.001 joules per centimeter squared up to 10. So look at that range. Then there's also been shown that the red or near infrared as low as 3 or 5 joules per centimeter squared, which fits right in between the ranges from the quote above, showing that 3 to 5 will be beneficial in vivo, so obviously in real life studies, but large doses of 50 or 100 joules per centimeter squared will lose the beneficial effect and may have become detrimental. That actual quote comes from that graph that I had earlier on. So that's the exact quote from that paper. And it is accepted that laser therapy conforms with the Arndt-Schultz law, or hormesis as we know it today. A therapeutic window of laser doses may exist between energy densities of 0.5 joules per centimeter squared and 4 joules per centimeter squared. Doses above these may result in bioinhibition. So now you've looked at that and you go, look at all those ranges. So why is there such a large gap in those different joules per centimeter squared when we look at the research? And the answer is the electron volt. We can't use a uniform dose, like the idea of joules per centimeter squared, because it's not taking into account the energy of the wavelength that's being used. These formulas are all being calculated on distances, the area that you're actually trying to treat, and then the wattage of the actual laser. It's not taking into account the actual electron volt, the color of the wavelength. So this is why we see this variation in range. But if we just go back to that very top one, and we can see here that most of the ranges there are showing you from 0.001 up to say 10. That's giving you the ranges of what's considered going to be biostimulation. It's going to have a positive effect. And we're saying that anything over that may start to create biostimulation according to the literature. And of course, things that are getting into the 50 joules per centimeter squared. One thing actually I would like to clarify right now on that is just this understanding of joules and watts, because it is one that does come up, and I haven't really got any slides on it. So let's just talk about it real quickly. When you hear the word watt, 1 watt is 1 joule per second. All right, so we can just start to do our math with that. So if we've got that top, let's just use the top one right now, because I'm going to use that later on in the slide for an example. But if I've got 0.001 up to 10 joules per centimeter squared, if I've got a 10 watt laser, that is 10 joules per second. So if I put that laser of 10 watts on that area and held it there for 10 seconds, I have now imparted 100 joules. So now I've already gone into the bioinhibitory effects. Okay, so the wattage of the laser, watts equals joules per second. So you can use that real quick mathematical formula to be able to then figure out, obviously exceeding hormesis and having bioinhibition effects. Okay, so we talked about that, the electron volt. This is just jumping on a website and using one of these like physics sites just to show people that photonic energy that we talked about earlier. This is where I got those numbers from before. So just using a 1 watt laser, 405 wavelength, and that is how much photonic energy. So when you're wondering where these numbers come from, it's just from one of these online calculators, obviously. So the flux being photons per second, and we can see just the extraordinary number of photons per second that there are. And then when we start to get down into our infrared ranges, we can see that electron volt 1.49. And what we talked about in those earlier studies is showing that we need to be in that range of 1.7 to be able to create a photochemical effect. So the example here I'm trying to show everyone is the joules per centimeter squared would be the same. So let's just give, for argument's sake, each of those circles is 3 joules per centimeter squared, or they're 5 joules per centimeter squared, or they're 1 joule per centimeter squared. They're all the same, but as we can see that the energy per photon is vastly different. So we can see our 635 on the left is 35% less than this 405 violet. The green is 30% less than the 405 violet in terms of the electron volts, 235 to 3.06, depending on that website I showed you before. And then our infrared is 50% less energy than this. So again, don't get confused now with energy versus power. Power's got to do with that wattage. Excuse me. So power's got to do with that sort of wattage, the joules per centimeter squared. energy's got to do with the electron volt, the wavelength, the color of our light. So here's an example I used. I took one of Erconia's presentations, and what they had done is they've done the calculation just to show you that idea of using an Erconia laser and just applying it to someone's forehead, showing the laser scanner is this distance, as we can see here, about 3 inches from the forehead, which creates the beam length. So if I showed you guys this again here, and we just put this on my brain here. So if I'm on my forehead there and I'm using that, okay, so if I'm at 3 inches, so 3 inches is going to be about, and that's a little bit beyond my fist, is about 10 centimeters. So that's about 10 centimeters away, which is a little bit further than what we're showing there. So when we look at that basic example in the picture there and what I just showed you, that using a 17 milliwatt laser, the treatment area is measure out the forehead. In this was about 3 inches, and that was from the body, and the actual is, which works out to be approximately 89.2 centimeters squared. So when we do our calculations for the milliwatts with that distance, if we use that previous article from earlier on that talked about stimulation could be as low as 0.001 up to 10 joules per centimeter squared, what you could see there is using a 17 milliwatt laser for 1 minute directly over the forehead at that distance would give you 0.0118 joules per centimeter squared. So we're now in that range of creating biostimulation. We're creating that stimulation, and in order to exceed the threshold, hormesis, and create bioinhibition, you would need to keep that laser on someone's forehead for over 14 hours to exceed the 10 joules per centimeter squared. So the one thing with the Erconia lasers and low-level laser therapy, the milliwatt low-level laser stuff, so 17 milliwatts, you would have to be holding these devices on areas for extraordinary long periods of time in order to exceed those biphasic dose responses. All right, so coherence versus non-coherent. So very simply, we're talking about broadband light and LEDs. So as we can see here, normal light or a light bulb. So broken it down, as it comes out of just a flashlight, light bulb, light comes out in all directions. Just think about, the lights that are above my head right now, coming out in all directions. Normal light is non-monochromatic, so it's not of the same single color. Okay, it's not the same single color. It's not all coming out at 635. You've got like white light, so you've got 405, 605, etc. So we've got all of those different colors. So it's non-monochromatic and it's non-coherent. Okay, now break that down. What does it mean a little bit more? We come to an LED. LED comes out in all different wavelengths, just like the LEDs we're putting in our roofs now. So it's all directions again, but LEDs come out in that single wavelength that's monochromatic, non-coherent. Okay, so when we look at a laser, laser's got the directionality to it. So obviously we saw here with this particular laser, obviously with their patented light beam, so we can actually see that straight line directly onto my forehead there. So it's monochromatic. I got the red being the 635 in this case. I got the violet being the 405. So I've got monochromatic violet. I've got monochromatic red. It's coherent, meaning all of those monochromatic photons are traveling in the same direction. Okay, so if it's non-coherent, they're not traveling in that same direction. So this particular study, if you look at the title there, only lasers can be used for low-level laser therapy. So non-laser light sources, lamps with or without filters, LEDs with or without a polarization, etc., cannot be used in low-level laser therapy because of their minimal efficiency. LEDs have their niche in a vast field of light therapy. For example, they're very successful used in photodynamic therapy. UV LEDs have good bactericidal effect, but to expect clinical effects similar to those obtained precisely in low-level laser therapy using low-level laser therapy from them may be a waste of time. So laser therapy, as the name suggests, should only be conducted with lasers, but no other light sources. And that's quoted directly from that article. I really want to start to break down now, because we know that LEDs work, we know that infrared works, we know that low-level laser therapy works. But when we start to get into the difference between laser now and LEDs, so the contribution of monochromacity or temporal coherence, monochromacity using that single color wavelength, the contribution of that is much more significant as it relates to light absorption. Okay, so using an LED light that's above my head, that is, from a certain extent, having a therapeutic effect, but because it's not monochromatic and directional, and obviously in certain wavelengths, obviously being a white light, the absorption of it is not going to be as good. So the contribution of monochromacity is much more significant, and illumination from the laser absorbed several times more actively than incoherent light with a larger spectral width. So laser light is absorbed more actively, so I'm going to have a better photochemical effect. What I'm going to just show you here is all the Zirconia studies. To gain FDA clearance, you are doing a randomized controlled, so placebo-controlled, double-blinded study. So Zirconia, in these particular studies here, we are looking at the 635 nanometer wavelength on those pictures there. So we look at the solid black line showing this was the subject group's pain level in this particular study. And this is a review of all of their pain studies, by the way. So this is a nociceptive musculoskeletal as it related to plantar fasciitis, neck and shoulder pain, low back pain. Yeah, they were the three, but obviously they've done the neck and shoulder one twice. So we've got these particular studies here. And so when we looked at all of the studies combined, this is where the pain study group started with their VAS scores. And then by the end of the laser treatment, this is where they got. What Zirconia used as their sham, as their placebo, was a 635 nanometer LED. So we are comparing 635 nanometer low-level laser, the Zirconia laser in the solid black, versus a 635 nanometer LED in the dotted line. So we can see the LED works, but it doesn't work as good as the laser because of that idea of the light absorption for the photochemical effects. All right, because it's not that directionality from the LED. We've got more scatter. All right, we're not going to be able to absorb as many photons. So the laser with that directionality, with that wavelength, we can see here the wavelength from the LED dotted line. We got improvement, but not as good as improvement as the laser. I want to come back to how we get clearance for that. Then when we look at following up these people months later, we can see that after the treatment ended, we can see that, yeah, LED got better, laser got better, but we can see that after the treatment, the LED people started to regress, whereas the laser therapy groups continued to improve. So there was ongoing therapeutic effect from the actual laser therapy because of those photochemical effects is the sort of discussion concept behind how that worked. Now, the same thing here, Zirconia has also got an emerald device that has got FDA clearance for fat loss, for circumference reduction. So what we can see here, again, is we've got our LED group, because that's the placebo that they used, got the exact same wavelength as the laser. So we can see the responses from the laser. So in the laser, there was a 3.52 inch reduction in circumference, and the laser had a 0.68, so 6 times better results with laser. In another study that they did, we can see here 4.6 inch reduction in circumference versus the LED, which was a 0.7 inch. So does LED work? Yeah, it just doesn't work as good as laser. So when people are trying to go, which technology do I want to use for the best therapeutic outcomes? When we start to look at the Zirconia research shows that laser is better than LED significantly. And those are important points for when we start to get into the recognition, and I'll show you this with some studies coming up in a little bit. So class 4 lasers, when we look at the FDA clearance for you guys can jump on the FDA side. I've got an example coming up on a couple of slides. So FDA cleared under the product code of ILY. The ILY category on the FDA website started as a heating pad and is expanded to thermal lasers, which are intended, and this is the quote, so class 4 lasers are intended to provide topical heating for the purpose of elevating tissue temperature for temporary relief of muscle and joint pain and stiffness, arthritis pain or muscle spasm, the temporary increase in local blood circulation, and or promoting relaxation of muscle. FDA has now made the ILY products exempt based on the device requirements of raising skin temperature to 40 to 45 degrees. So we understand how that works though now. If we go back, we know that those infrared wavelengths that classically most the class 4's lasers are using, we understand that that infrared wavelength is being absorbed by water molecules, creating that vibrational rotational effect, creates that photothermal effect, which creates obviously the heating that we feel. So now when we look at what the clearance is for FDA, is that for a class 4 laser to be cleared under FDA to go, yes, this is a class 4 laser, we give it approval, they need to show that their device can raise the skin temperature to 40 to 45 degrees. There's that photothermal effect. And then they get recognized as an ILY product code for providing topical heating. Now, again, I don't want to be cynical here, but that means class 4 lasers are being registered as an expensive heat lamp. Okay, so that photothermal effect, we know it has these positive effects, but they're being recognized to heat skin temperature up and provide topical heating for the purpose of elevating tissue temperature. So if we look, as an example, I jumped onto the website and just put in a search for one of the common lasers. Forget it, I'm not throwing anyone under the bus here. We can go in and search for anything. But there's obviously a common name of a class 4 laser that's commonly used. And we can see its classification is, it's a lamp, it's an infrared heating lamp for therapeutic heating. The classification code is an ILY, which we talked about on that previous page, and that's what it's for. And then, of course, if you go to the summary of all the things that's been showed for its clearance, what its uses are for, as an example, there's just one that you can go and look at, but you can put in any device. So you could put in Erconias, you could put in all the different types of other laser companies that are out there, and you can put in the search for it and understand how they're registered, what they've done to achieve FDA clearance. I don't want to get into this concept here of how the decision was made, substantially equivalent. We've got one, you can either do the research, or one, you can have a product that already exists and you can copy the specifics of it and put in an application for clearance based on being substantially equivalent to a device that already exists. So there's our basic differences when we look at FDA clearance. So let's start to talk about that idea of how raising temperature and one of the concerns with that we have. So we all know that if we're using a class 4 laser, because those photothermal effects, we need to move the laser because the raising temperature creates a concern as most proteins, DNA, RNA, membranes, and their integral structures start to unwind or melt at temperatures ranging from 40 to 100 degrees Celsius. The result is denaturation or loss of function. These effects, accompanied by bond destruction and membrane alterations, are summarized in the single term hyperthermia, ranging from approximately 42 to 50 degrees. And if such hypothermia lasts for several minutes, a significant percentage of the tissue will already undergo necrosis. Now, the interesting part, remember that the FDA, a thermal laser device, a class 4 laser, requirements are that it needs to raise the skin temperature to 40 to 45 degrees. But if we look at mechanisms and physiological processes based on the literature, we know that we actually don't want to do that to our tissues. We don't want to be raising the skin temperature to 40 to 45 degrees for long periods, as we can see by that particular study. Summarizing the results of this study, it was established that free radicals are produced during infrared irradiation of the human skin. This effect was demonstrated in vivo by resonance Raman spectroscopy measurements and confirmed by electron paramagnetic resonance spectroscopy investigations showing that heating to approximately 41 degrees Celsius, free radical formation was almost doubled and antioxidant power was reduced to about 50%. So again, just going into photothermal versus photochemical effects, when we look at photobiomodulation as that umbrella term, and we start to look at photochemical versus photothermal effects, the literature suggests the effects that are therapeutic to help humankind appear to be the devices that can impart photochemical effects, not photothermal effects. Now, this one was just to polarize it for the purpose. We understand that there are different medical lasers that we can use for obviously surgical procedures. So the aim of this study was to compare the efficacy of 4 diode laser wavelengths. So as you can see, they're all in the infrared wavelength there for the ablation of soft tissues. They wanted to see what the time was to ablate soft tissues. And so you can see there in the highlighted blue, if we use a 2-watt laser or a 4-watt laser, it would, let's just go with the 4-watt laser, it'd take you 150 seconds to perform the excision. So they were obviously going into try and go around a tooth there, oral surgery. So how long would it take? Now, if we're using a 10-watt laser, obviously the time's going to decrease even more. If we use a 20-watt laser, that's going to decrease even more. So we can see 2-watt compared to 4-watt. If we went to a 10-watt laser, 20-watt laser. So the idea of these class 4 lasers, the higher powered lasers, we are using them more for obviously surgical medical procedures, for the ablation of tissues, for cutting of tissues, etc. All right, and then of course, one of the other final problems with this is that we see, and again, this is where the misinformation starts to come into it. Again, sharing some of the journeys that I've been on about where I was getting confused, and you jump on websites, you see various clinicians explaining what they're doing with their lasers, etc. And so when we look at this particular letter that was sent from the FDA to a class 4 laser company, the FDA has obviously sent this letter to them. The FDA has written, devices under the ILY product code, which are class 4 lasers, are intended to provide topical heated to the treatment area. However, evidence collected, when they went and investigated that laser company, just demonstrates that your firm is marketing these devices with intended uses for tissue regeneration, healing, improved vascular, etc. And they were all a list of things that that company had said that they could do. Now, this is again that poor clarity, misinformation, because we're going to see laser companies, practitioners out there that have maybe been given information or not the full story of the information, being shown research about LEDs maybe, or about low-level laser therapy maybe, and then we've got a laser company that doesn't use those wavelengths or doesn't use that milliwatt, and they're promoting that as evidence for their product. And again, I don't want to say it's lying, but it's misinformation. The information's true. They're saying, yes, this is how this particular research showed that this helps with, in this particular list of things here, it's helped with nerve repair, or it helped following dental surgery, or it helped with these types of repairs. But that research was probably done with some other form of LED or low-level laser therapy. Obviously, if the FDA is following up on them, the research wasn't done by class 4 laser. So the misinformation that's out there, the poor choice of words that's within the literature, photobiomodulation, and yet that systematic review I just happened to polarize used all infrared wavelengths. That's not fair. That's got nothing to do with photobiomodulation as an actual therapeutic choice, because that doesn't include LEDs, that doesn't include low-level laser therapy, it doesn't include just talking about specific wavelengths. So hopefully we can start to see the differences between these various things. So the FDA clearances that exist just from Erconia alone, as we can see there, there's 20 different FDA clearances that Erconia owns. We've got neck and shoulder pain. They've got pain post-surgery after liposuction. That became interesting because this is sort of how the fat loss device was created, because as part of the helping with the pain, they showed that the Erconia laser was actually liquefying the fat. And when the people were going in to do the liposuction was easy. This is how that one started, the research of that. We've got acne there. We've got obviously pain post breast augmentation surgery. We can see the body contouring of fat. arm circumference reduction, reduction of cellulite. You can see there's all the lists, and of course you can jump into the literature and look these up. But where I want to just go into is a couple of them as it applies specifically for us and how we can use the evidence for some of these pain applications. So when we look at the FDA, NHN, remember from webinar 1, is sort of a non-heating, non-thermal laser. So that is what low-level laser therapy gets recognized as to get an FDA clearance. It's a non-heating, non-thermal device. It's a photochemical device. So the different low-level laser FDA indications for pain, of the 15 indications that exist for pain for FDA that are cleared, Oconee has obviously done 9 of the actual research studies. And again, I bias myself to the literature and bias myself to the evidence. I try and be as evidence-based, evidence-informed as I can be. And again, having a chance to use their technology and see the clinical effects, which I want to share a couple of case studies when we get to webinar 3. That was what got me most intrigued when I saw those clinical effects myself. And then the fact that the Oconee group had been the group who have done the research, had done and keep investing the money into the science to understand how technology works. How do we make their technology even better? Hence, they've added violet to the red. Originally, it was all just red, as we can see in here. Originally, they just did neck and shoulder with red. Then they added the violet and showed that it worked even better, which we talked about in webinar 1, and we're going to get into now. But we can see plantar fasciitis, low back pain, overall post-operative pain, overall musculoskeletal pain, and again, biased again towards that literature. So what have we got for evidence-based clinical applications using the EVRL? So we talked about the very basic protocol in webinar 1. We can set our frequency settings there, which is just how the frequency of the light, of course, is basically moving there, which is why you can see that flashing light. And in this particular case, I think the violet is set, because we'll talk about neurology stuff next module, but that's set to 1 and 10. So you can see 1 hertz, 1 sort of flash per second, and then you've got the 10 hertz there, whereas the red there is 40/60. Talk about those more. So the pain settings, when we're using pain, so basically anything musculoskeletal, the settings have been used as 9, 16, 42, and 53. Basically about 10 centimeters is that sweet spot for the distance. You can also use that laser beam as a guide. So if I wanted to do my whole forearm, obviously if we say 10 centimeters is about there, but I could cover that whole forearm because of the patent optics that Oconee has and how it keeps that narrow beam to keep that photonic energy directed into the tissue. I could move closer to cover that whole area. So we can use that laser beam as a guide. Obviously, we position the laser in a perpendicular orientation, which means more photons are being directed to the tissues for better absorption. 10-minute treatment duration is your basic protocol. Just point and shoot over the area that you want to treat for 10 minutes, and your minimum treatment duration is 2 minutes. The Oconee website and the YouTube channel here has got other ways that you could enhance your treatment with movements, okay, passively, actively. Then if we go to the neck and pain protocols from Oconee, from where they've got their FDA clearances, we can see that they're using treatment transcranially on the top of the head. Then they're working down the ear, shoulder muscles, so neck, posterior, anterior, both sides. Then they're treating the anterior shoulder as they're moving it into external rotation. They're doing the posterior as they're moving it into shoulder adduction. They're obviously doing the neck with movement there as well, doing all of these things on the right and the left side, and that's a whole 13-minute treatment protocol. So that is what they did to get FDA clearance for the neck and shoulder pain treatment. They did it with the red laser, then they did it with the red and the violet laser using the exact same protocol, showing that the red and the violet had an even greater pain analgesic reducing effect, plus range of motion, plus functional reported outcomes that were better than just using red alone. Then the low back study, one of my friends and colleagues was the primary investigator on this one. And so the low back pain study they used was just using the red wavelength, and they used 8 20-minute treatments applied to the lower back region So it was 2 treatments per week for 4 consecutive weeks. And they just put the laser over the back, side areas, covering that sort of whole lower back area. As we can see there, the mean VAS scores decreased from 36 from the laser versus 8. Now, I'll show you a couple of things of how you get FDA clearance in a second. So we can see that difference there of 27.9 points. Remember, what's the sham Erconia uses? They use an LED of the same wavelength. So the laser at 635 versus an LED at 635. So the difference, you got improvements with the LED. Yep, you got improvements, better improvements when we're using the laser. Then the plantar fasciitis. So far we've got neck and pain that we've got evidence for that you can go, yeah, I can treat neck and pain with laser. I can treat low back pain with laser. And again, that's specifically talking about a 635 nanometer wavelength. The plantar fasciitis treatment protocol, as we can see, 2 treatments per week for 3 consecutive weeks, total of 6 treatments. If I just give you guys a general overview, if someone's coming in with acute pain, you're generally going to want to treat for 6 to 8 treatments, 2 to 3 treatments a week. The research always seems to be 2 treatments per week, but 6 to 8 treatments for acute, 10 to 12 treatments for chronic, as just a general guideline. And of course, you want to see that people are giving subjective and objective testing improvements to warrant continuity of care. So if they're not getting better, we may not be using the laser to its best ability. So if you're just doing point and shoot, and we'll talk about this more in webinar 3, we may want to go to what the website shows, where maybe we want to get people moving. So instead of point and shoot, that hasn't been working. They're not reporting any changes. I've done 4 treatments and it's not really getting any better. Maybe I change gears a little bit here and I start to add movements into the actual therapy. Maybe I start to do things called swimming upstream or swimming downstream, where we might start to treat local areas, then we might start treating nerve roots, cerebellum, parietal cortex, frontal lobes, the mapping aspects of that body part, and combine it with movements, combine it with vibration stimulation. We're going to go into these in webinar 3. All of these so far, though, are very basically sort of point and shoot, but we have seen the complexities that are involved in the neck and shoulder one, where they went brain, they went wanding through here, they went wanding through the arm and making movements. So we can see already in the literature, there's a couple of combinations here. Most of the ones I'm sharing right now, they're all just point and shoot. So we can see here the low-level laser therapy was 10 minutes applied across the top of the foot, basically the Achilles, and then the plantar fascia insertion onto the heel. So they were the areas. So 10 minutes total treatment time. So you could look at that and you go, well, break it down, 3 minutes on the top, 3 minutes on the bottom, 3 minutes on the back. And as we can see there, that decrease from 67.8 at baseline to 6.9 at 12-month follow-up just from laser therapy. And then the overall summary, we shared this in those graphs earlier. You've seen that graph already. So showing plantar fasciitis, showing low back pain, showing the neck and shoulder pain. When we put it all together and you're comparing it to NSAIDs, LEDs, opioids, etc., between the different groups of treatments, mean VAS scores decreased 45.4% for laser to 15.1 for the sham, which of course is LED in the sham for Erconia. Among the subjects receiving low-level laser therapy, 69% achieved individual treatment success, while subjects receiving the LEDs, 27 individual treatment success was achieved. Now, this is the point I wanted to highlight here, this 42% difference. So in order to achieve the FDA clearance, they had to show, Erconia had to show that they were beyond 35% better than whatever they were being compared to. So they showed that they were 42% better. So they get FDA clearance to demonstrate that they're at least 35% better than the sham. Okay, so that is the part of like FDA clearance. So all of our references for today, they're all there.
Thank you very much for that, Brett. As ever, a lot of information there, and you know, we answer any inquiries that people want to ask. So if you've got any questions that you want to submit post this event, then please do get in touch with us. But before we let you go, The date for the third webinar is Tuesday, the 15th of November. We are also going to be at the Chiro conference this weekend in Sydney. For those chiropractors that are able to attend, please do come along and say hello. Myself and the lovely Cheryl will be with us. So yeah, thank you and good night.